Welcome to the lecture block of day 4. Let me introduce today's first speaker, Merzuk Kaltak. Merzuk Kaltak is a true native in VASP. He started contributing to VASP 10 years ago during his PhD, which he did under the direct supervision of Georg Kresse. After a short excursion into the world of lithium-ion batteries during a postdoc, he could be convinced to join the VASP software company as a developer. His expertise lies in algorithms of the low-scaling GW method and the random phase approximation. With that, he made VASP attractive for applications to materials with some electronic correlations, where DFT alone fails. Today, he will give an introduction to the GW method as it is implemented in VASP. Merzuk, go ahead.
Thank you, Marie-Therese. Thank you for the kind words. Okay, so this lecture block is dedicated to the GW and the random phase approximation. And in part 1, I will cover the GW approximation. The following lecture is subdivided into following parts. First, I give a short introduction to basic concepts of quantum field theory. Specifically, I will explain what the Green's function is and how it is connected to its self-energy. I will demonstrate how physical observables, like for instance the band gap, can be extracted from Green's functions using the GW approximation, and I will present the most important GW algorithms available in VASP. Let's start with a short introduction to quantum field theory. First of all, don't worry if you don't understand every detail in the following. The main idea in GW and actually also RPA boils down to something that you are already familiar with, namely the one electron picture of quantum mechanics. Okay, let's look at ways how to describe a system of interacting electrons using a one electron picture. So in Kohn-Sham DFT, the Schrödinger equation consists of the kinetic term, the external potential, the Hartree potential, and the exchange correlation potential. This potential is local in nature and depends only on one space coordinate. The space coordinate that the solution of this equation, namely the orbitals and the orbitals depend on, and is insofar important because if you consider hybrid functionals, like for instance HSC, you replace this local potential by a function that is non-local in nature. So it depends now on two space coordinates. This increases computational complexity, of course. However, in GW, you go even one step further and replace this non-local functional or non-local function, by a frequency-dependent non-local function. So this here is the so-called self-energy, and the main part of this talk is dedicated to methods how to calculate this object using methods from quantum field theory, specifically Green's functions. Now, what is a Green's function? A Green's function is also known as a propagator and describes the propagation of particles from one space-time point to another point. Consider, for instance, this simple hopping of an electron from one side to another side. In a space-time diagram, this hopping would correspond to this straight line going from point 1 to point 2 using this notation here. And the movement of this particle in this space-time is described by this function called the non-interacting Green's function, or also the free propagator. Now, the idea in quantum field theory is that this free electron is surrounded by an interacting quantum field. This field allows for spontaneous creation of virtual electron-hole pairs but it also allows for the spontaneous annihilation of these pairs. In other words, these virtual electron-hole pairs have a finite lifetime. For instance, let's assume a virtual hole is created at space-time point 4, and a virtual electron is created here at space-time point 3. Now, apart from having a finite lifetime, these virtual particles also interact with the original free electron via the Coulomb interaction. Okay, so this Coulomb interaction has this form we are already familiar with and is instantaneous in time. Now, apart from interacting, these virtual particles can also move and propagate. And this propagation is again described by Green's functions, namely by the free Green's function. Here, for instance, an electron moves from point 3 to point 4 and is described by this object, while the corresponding hole moves into the opposite direction. On a macroscopic level, there is no way to distinguish the original free electron from virtual particles. So actually, the collective movement of these particles, the electron, including the virtual hole and electron pair, should be imagined as the propagation of a dressed electron, a so-called quasi-particle. So this quasi-particle exists only for a finite amount of time. It is heavier, therefore moves slower, but has the same charge as the original free electron. And again, the main idea of QFT is that one can only observe these quasi-particles or so-called dressed particles. And this means that the propagator of these quasi-particles, denoted by capital G, or the interacting propagator, is the main quantity we are interested in. What one should bear in mind is the fact that there is a symmetry known as CPT symmetry, which goes back to Feyman and Stückelberg. And this symmetry is insofar important because it tells you that there is in essence no need to distinguish between electrons and holes, because electrons and holes are described by the same equation in QFT, the Schrödinger equation. Using this Feyman-Stückelberg interpretation of quantum field theory, propagation of electrons and holes are described simultaneously with the so-called Feyman propagator. So what is the Feyman propagator? It's nothing else than the free Green's function. It describes the propagation of a particle from 1 to 2. And this propagation can be separated into two contributions. So the first contribution is not zero if T2 is later than T1. So the first term then will represent an electron moving from R1 to R2. And the corresponding expression for the propagator is here. You see only occupied states contribute. If T1, however, is larger than T2, so T2 is earlier than T1, then the propagator describes the propagation of a hole going from R2 to R1. And you see that the corresponding explicit expression has only unoccupied states. In quantum field theory, it actually also doesn't matter at which points the virtual particles are created, but it only is important how the interaction process looks like. These processes are usually visualized with Feyman diagrams. On the left-hand side, you see an example for such a process that can happen between, for instance, point 1 and 2. And on the right-hand side, one typically, there's a picture how one typically describes this process in terms of a diagram. And these intermediate points 3 and 4, they have to be integrated out. And if you translate these diagrams into an integral, you end up with basically something like this. Now, using Feyman propagator is insofar helpful because only the topology of the diagram is important? This, on the other hand, reduces tremendously the number of diagrams that you have to consider. Why is this important? Because we have seen how a virtual electron hole pairs stress free electrons and described the interacting propagator. However, in practice, you have infinitely many possible interactions that can happen between point 1 and point 2. So you have to actually take all possible processes into account. And here are only shown a few examples, the lowest order contribution, so to say. So here we have this Hartree bubble, or here we have the first order in the RPA and higher order terms. To bring structure into this chaos, the idea of Dyson is of importance. So Dyson noticed that a process can occur repeatedly, and he wanted to take this fact into account. So Dyson had the idea to structure these repeated processes and include that in such a irreducible self-energy, he called it. So this blob basically contains the sum of all, under parentheses, irreducible ways the electron can interact with itself. That is the sum of all irreducible diagrams. Specifically, in order to avoid double counting, one defines the irreducible self-energy as follows. So sigma is the sum of all diagrams that do not separate into diagrams already accounted for if we remove one arbitrary propagator length. Okay, sounds tough at first, but actually isn't. For instance, let me explain this in hand for this example. So the second diagram is not irreducible because you can remove one arbitrary propagator line, for instance, this one in the middle, and you end up with 2 times the first diagram. So that diagram is not included. The same actually for this diagram. So if you cut it through, you end up with this irreducible diagrams times 2, and so on. Now, lower order diagrams in the irreducible self-energy look like so. Using this definition for the self-energy, Dyson showed that the interacting Green's function, or the dressed Green's function, obeys an equation that has this form. So this is the object we are looking for, and it consists out of the free propagator, the Feyman propagator, and then you add repeated insets of this self-energy in between 2 propagators. So 1, 2, and so on. If you rewrite this in terms of functions, you will see that this is kind of an geometric series that can be carried out. And after rewriting, you end up with the famous Dyson equation for the interacting Green's function that connects the non-interacting Green's function with the interacting one via this self-energy. Now, unfortunately, in practice, the self-energy is not known, and one has to rely on approximations. However, I will show you that this approach is really powerful because the lowest order terms already give you something that is Hartree-Fock. So let's first consider the Hartree contribution. So this is the first order term. So there are just 2 first order terms, and one of them is the Hartree contribution. If you convert this contribution to an integral and carry out this integral, you will end up with the Hartree potential. Now, this similarly for the exchange contribution, which is the other first order term that is present in the self-energy. If you translate it into a diagram and evaluate it, you end up with this expression that is the exact exchange potential. So already by including more diagrams than first order, we end up with something that is post-Hartree-Fock. And in fact, it turns out that you can include all bubble diagrams like those here up to infinite order. And this approximation is known as the GW approximation. So including the first order terms and all bubble diagrams gives you the GW approximation. So this, yeah, So Lars Hedin introduced this approximation, and he used an idea of Hubbard. So Hubbard had the idea, on the other hand, to introduce the analog of the addressed Green's function, but now for the interaction. So he introduced this screened interaction W, which is connected with the bare Coulomb interaction via a polarizability. So here, for instance, we include only these bubbles between two interactions, which ends up with the random phase approximation. But in essence, you have, again, something that looks very similar to the Green's function, but now for this screened interaction. And you can evaluate this geometric series to end up with the corresponding Dyson equation. Now connecting the bare Coulomb interaction via this polarizability with the screened interaction. And now this screened interaction can be seen as an interaction between quasi-particles. Now, as I said, including only these bubble diagrams here, you end up with the random phase approximation. And with that, you can write very compactly the GW approximation to the self-energy with this diagram, which includes the first order exchange term and then all bubble diagrams up to infinite order. However, if you include all diagrams, probably a better way to approach this topic is to use Lars Hedin's equations. So if you translate these diagrams into equations and define 5 objects, you end up with a set of 5 coupled equations called the Hedin's equations. So this set of equations is equivalent to an original problem and can be solved iteratively. So in the first equation, you determine the Green's function, then the polarizability, followed by the screened potential, then the self-energy, and finally the vertex function. So the idea is here, you start with a first guess for the Green's function, compute the first approximation to the polarizability, continue with the screened potential, self-energy, and then this guy here would introduce more and more diagrams after each cycle. However, as you can see, this looks really complicated. In fact, it's also impossible to solve exactly, except maybe for trivial cases. So that's why Hedin actually proposed this GW approximation with only this bubble diagrams in the screening. And this GW approximation assumes that you actually forget about the vertex, and then it cancels out here in these integrals, and you end up with a reduced version of the equations now for the GW approximation of the system. So once again, we have to determine the Green's function, the irreducible polarizability, the screened potential, and the self-energy. Now, in principle, these equations should be solved again self-consistently. And the best way to do this or to deal with this is to get rid of these integrals here. And that usually is done by transforming this object from space-time into reciprocal space and frequency. Then you get rid of these integrals in these 2 Dyson equations. And you end up with something that looks like this computational scheme that we have recently implemented in VASP. So you start here with the Green's function in the space-time domain. Then you build the polarizability in the same domain with the product of 2 Green's functions. Then you make a fast Fourier transform to reciprocal space and frequency domain. Solve in this space the Dyson equation for the screened potential, and then reverse the operations to end up with the self-energy and so on until you have an updated version of the Green's function where you can close the loop here. At the end of the day, If you do this self-consistently, you will end up with an interacting Green's function. Now the question, of course, is what do you do with it? So what can you do with the Green's function in practice? For that purpose, let's consider the non-interacting Green's function in frequency domain first. So you perform a Fourier transform of the Green's function in time, and then you end up with an expression that looks like this here. So here, these orbitals, they are usually taken from the Kohn-Sham equation, and the energies are usually the corresponding energies. Now, the interesting part here is that these energies are nothing else than the poles of the Green's function. Okay, one also actually talks about G as being the resolvent of the Kohn-Sham Hamiltonian. Okay, so and the condition for these poles can be written in an operator form like this. So what's interesting here is that the same holds true for the interacting Green's function. So if you solve the Hedin's equations and you get a new Green's function, you're interested in the energies of the quasi-particles, and they are determined by a similar equation, namely, but this time for the interacting propagator. And you have to solve this equation here to get the poles of the Green's function, which are the quasi-particle energies. Now, this time, the Hamiltonian, however, is depending on these poles, so it's frequency dependent, so to say. The usual way to handle this is to separate this frequency dependent self-energy into two parts, an Hartree and an exchange correlation part, and then to formulate the corresponding condition for the poles as an generalized eigenvalue equation. And that one here is the one I've mentioned on the very first slide, which is a generalized eigenvalue equation with a non-local frequency-dependent potential. Now, the conditions for the poles for this equation can also be actually given by this expression, but what I wanted to remind you of is that if you replace this self-energy now by Hartree-Fock, so you get rid of this energy dependence, you get the exact exchange, you get the Hartree-Fock equations. And similarly, if you replace this function by a local one, which is energy independent, you get the Kohn-Sham eigenvalue equation. So this is quite neat and comforting. Okay, in the following, various flavors of GW will be discussed. And let's start with one and assume that you're only interested in the quasi-particle GW energies. So only these energies are of interest to you. And actually you want to calculate them after doing only one iteration in GW. So that's kind of, yeah. A good way to obtain these energies with minimal effort is the so-called eigenvalue G0 W0 method. Okay, so this method focuses on the generalized eigenvalue for the quasi-particle energies. So that one we have seen on the previous slide. And in this operator form, the locations of the pole in the Green's function are actually, as I said, sorry, given by this expression. Now, the eigenvalues here appear on both sides of the equation. So we have here on the left-hand side and on the right-hand side, we have the energies of the quasi-particles that we want to obtain. Now, typically, this equation is solved by linearizing this object up to first order around the Kohn-Sham energies. So if you do so, you end up with this approximated form for these energies. And note that you here never update the orbitals. No, sorry. And this equation is solved furthermore, by defining the renormalization factor, then you can rewrite this equation into this form. And then you have the updated versions for the quasi-particle energies in this method are obtained from the original Kohn-Sham energies times this renormalization factor times this difference of these two energies. Note that in this method, the orbitals are never updated. So only one gets new 1 electron energies. Now, the calculation steps for this eigenvalue G0 W0 method are depicted on this slide. So idea is you first start with the polarizability and calculate it directly in reciprocal space and frequency domain. Then the Dyson equation for the screened potential is solved. And afterwards, a convolution with the non-interacting Green's function is performed to obtain the self-energy. Now, due to the form of G in the first step, so it's the non-interacting Green's function, this is essentially a Hilbert transform. And afterwards, you solve the generalized eigenvalue equation to obtain the quasi-particle energies. So this is just one shot, okay? Now, what are the computational bottlenecks of the eigenvalue G0 W0 scheme? Yeah, a computational bottleneck is the direct computation of the irreducible polarizability using this formula of Adler and Weiser. So this expression involves a sum over occupied and unoccupied states and scales with the 4th power of the system size, and actually also quadratically in the number of k points. However, an even larger bottleneck is the determination of the self-energy, which in the Kohn-Sham basis has the following form. This form here follows from the Hedin's equation for the self-energy as a convolution, where you now have only the interacting Green's function inserted here. So if you plug that in, evaluate this integral, you basically have this form. Okay, how does an actual G0 W0 calculation in VASP look like? It is a 3-step procedure. So here are the main Inca tags for each step. So first you determine the DFT ground state, then followed by another DFT step where you now increase the unoccupied or virtual space using a large value for n bands. Note that you have to diagonalize the Hamiltonian exactly. So you perform an exact diagonalization. And then you actually perform the actual GW step in the 3rd step. So here you use the same number of bands and select the corresponding algorithm with this EVGW0. In older versions, we called this G0 W0, and set this name to equal 1. Okay, so additional Inca tags that you should take care of when doing GW calculations are, for instance, the cutoff of the orbitals, so the energy cutoff of the orbitals. Then, of course, n bands. So as I said, n bands should be large enough for the GW step. Typically in production runs, I set it to the maximum number of n bands provided by this cutoff. And that can be looked up in the outcome of the DFT step by looking for this line. Then the number of frequencies for the Hilbert transform is set by n omega as a default value of 50, which is pretty good for a rough estimate. However, in production runs, I would increase it. And even for small gap systems, higher values probably are required. However, this comes with only little performance penalty because it goes more on the heavy memory side. Now, 2 more tags which might be important in cut GW. So this is a cutoff for the polarizability. The property that the polarizability, or also called response function, has is that it converges faster with the cutoff. So this is why the default value is smaller than the cutoff for the orbitals. And what also might be important is for extremely accurate calculations is that you maybe need to use norm-conserving potentials. But bear in mind that the corresponding cutoff is larger than standard GW potentials. Now, after one eigenvalue G0, W0 calculation, the outcome will contain an output of the following format. So for each iteration, I forget about the iteration, for each K point, I mean, there's a table similar to this one printed here. So the first column denotes the band index. The second column, the corresponding Kohn-Sham energies. And the third column is probably the interesting column for you because it contains the quasi-particle energies for the corresponding band. And together with this column here that describes the occupation of the corresponding state, you can calculate the band gap by subtracting the value of the conduction band minimum from the valence band maximum. Okay, and you hopefully, when you do that, and you hopefully end up with something that looks like this plot. So here we have a comparison of EVG not W not band gaps with the experiment. The values are plotted such that points closest to this red line represent the best agreement with experiment. There are 3 sets of band gaps shown. So blue dots correspond to the band gap for DFT, and the empty triangles correspond to the single shot GW band gaps. It can be seen that GW single shot only improves already systematically compared to DFT. Okay, but what are these filled triangles? Yeah, so you see that they actually have an even better agreement with the experiment. These values are calculated with a similar method, but which is actually taking into account self-consistency in G. So this is the so-called EVGW zero method. So the idea of this approach goes back to Hybertson and Louis and is originated from the fact that the Dyson equation for the Green's function is hard to obtain. So one might say that this approach neglects proper dressing of G and uses the quasi-particle energies of the previous iteration to only shift the poles of the non-interacting Green's function. Then this Green's function is used to recompute the self-energy as so. Note, however, that the orbitals in the Green's function, as well as the screening, are kept on the Kohn-Sham level, so you don't change that. After each iteration, you will get a new set of quasi-particle energies calculated from this equation here, where and this process is then repeated several times. The scheme of this method can be illustrated as follows. So again, you start like in the single shot GW calculation from the direct computation of the polarizability and do this one shot G0 W0 approach. You get a new set of quasi-particles and you interpret these quasi-particles as the new poles of the non-interacting Green's function. Then you recalculate the self-energy, but with the screening from the first step, you don't change that, and then you iterate here several times. And in VASP, to select this algorithm, this is again a 3-step procedure. Here are the main Inca tags for each step. First, again, the DFT ground state is calculated. Then you increase the virtual space by increasing the N bands, as in the single shot approach, and perform an exact diagonalization. In the third step, the actual self-consistent GW calculation is done, again with the same tag like for the single shot one, but now you set NELM to a higher number, for instance 4 to 10, and NELM will give you the number of iterations that should be performed in G. The same Inca tags as for the single shot eigenvalue G naught W naught should be tested for convergence, and I will not really go into detail here because nothing is really different. However, the output looks slightly different. So after several iterations, the outcar file will contain an output of this format, and each iteration here now, each iteration in G will have its own block of data that looks like so. So again, the first column is the band index. Then we have here not the we have the quasi-particle energies from the previous iteration. So in the first one, it is these are the Concham energies, but in the third iteration, they correspond to the one from the previous iteration. And what's interesting for you is again this third column where you have the quasi-particle energies of this iteration, together with the occupancies of the bands. You can determine the band gap and end up hopefully with these black triangles, which are really in good agreement with the experiment. So one sees that the single shot approach is already quite good, as I said, but the partially self-consistent one is even better. Now, what happens if we update the orbitals of the Green's function as well? Because until now we have kept them on the Concham level. So can we somehow update these orbitals too? And the question is actually, we can do that. Schilfgaarde and Kotani were the first to propose this back in 2004. And they used an hermetized version of the self-energy, which makes this generalized eigenvalue equation Hermitian. So because of that, you can then solve this equation using diagonalization, like from LAPACK, for instance, and you get a new set of energies and orbitals. So we improved this slightly by linearizing this self-energy around the previous quasi-particle energies of the previous iteration up to linear order, and then reshuffle a little bit and define such an symmetric operator to end up with a similar equation. Anyway, at the end of the day, you get new orbitals and new energies, and you use these orbitals and these energies for the new Green's function, the new non-interacting Green's function in the iteration. However, note that you are still avoiding the solution of the Dyson equation. So you only update the orbitals of the non-interacting form of the Green's function. The Inca tag the Inca tags for this algorithm are very similar to the previous ones. So again, the 3-step procedure. Now in the third step, you select this algorithm with quasi-particle GW0. And with NELM, you set the number of iterations you want to perform in G. How are the band gaps with this approach? Yeah, in summary, there is only little improvement compared to eigenvalue GW0. Now the black triangles correspond to the band gaps of this method. and the shaded triangles are the one from the partially self-consistent GW. So in all, they are very similar. I would say maybe slightly, on average, slightly larger band gaps, but yeah, very similar anyway. However, the density of states might be different compared to other GW methods, especially here, for instance, if you look at this lanthanum aluminum oxide, you have here in the conduction band a different density of states than for the other GW method. Good. Now, the next question we want to address is what happens if we also update the screening GW? Because so far we have only updated the non-interacting form of the Green's function, but kept always the screening frozen at the Kohn-Sham level. Yeah, and how can we do that? So self-consistent GW calculations in VASP can be done, for instance, with this eigenvalue GW approach. So the loop here is closed as follows. So you start here, again, from the direct computation of the polarizability, go over to the Dyson equation, so go over to the screened interaction, then the self-energy, get new quasi-particle energies, update the Green's function, and now recompute the polarizability with this Green's function, and then close the loop and iterate, okay? So this would solve the GW Hedin's equations self-consistently, at least approximatively. Now the question is, how does the band gap look like after we close the self-consistency loop? Yeah, before we address that, the method is simply selected again by a 3-step procedure and with this algo tag. So there's nothing really different compared to the other methods. However, the band gap is actually quite disappointing. So the results are really not that good. The band gaps become too large when compared to the experiment. You see that now these black triangles are the band gaps of the method, and they are way too too large. One could argue that the reason is the fact that we never solved the Dyson equation for the Green's function. So neither the eigenvalue nor the quasi-particle GW approach is doing this. So maybe we can account for this inconsistency by really trying to solve the Dyson equation for the Green's function. Recently, we have implemented a complete self-consistent GW approach, which can do that. So that is solving the Dyson equation for the Green's function is now possible. So I've discussed that already, but I'm going to do it again because it's actually illuminating how these steps work. So first you start with G, with the Green's function as a first guess, perform the space-time product here of two Green's function to get the polarizability. Then after a fast Fourier transform to reciprocal space, solve the screened interaction and go on and repeat and update the Green's function. And then you do again a loop, a step, and so on and so on. Now this procedure scales like the third power, so scales with the third power of the system size n, but might be slower for smaller systems because of many FFTs involved. So the Inca tags are very similar to other GW calculations, except that one selects the algorithm now with algo equal GWR. Bear in mind that this method does all calculations on the imaginary axis, which requires only a small number of sampling points on these axes given by an omega. So typically 16 are more than enough. I will talk about this in the RPA section in more detail, but for now, bear with me a second. So you just have to take maybe into account that if you do this kind of calculations, the same Inca tags should be checked as for the other GW implementations, but with a smaller number of wear and omega. Also, in case the system is a metal in DFT, one should use Fermi occupancies by selecting isomere -1 in all steps, and finally switching finite temperature mode in the GW step. Again, I will talk about this more in the RPA lecture. Okay, now after a successful run, the outcome will have now more data than the previously discussed algorithms, and the output will look similar to this one. So again, we have the Kohn-Sham energies here in the second column. And now, however, there are two sets of quasi-particle energies printed. So the first block corresponds to the energy obtained from the linearization of the self-energy around the Kohn-Sham eigenvalues. So this is very similar, it's actually the same to the algorithms discussed before, where all calculations are done in the reciprocal space. However, now you also have another block of data that contains the quasi-particle energies as roots of the denominator of the Green's function, that is the poles of the Green's function. So you take into account the full frequency dependence, but in reality, they are very similar. So there's not a big difference between them. Good. So how does the result for the band gap look like when you switch on this self-consistent GW algorithm? Yeah, again, it's actually not changing a lot. So it's actually changing nothing, to be frank. So you have, again, two large band gaps. And this definitely demonstrates one thing, namely the shortcomings of the random phase approximation. So with other words, the chosen screening in GW is bad, in particular for the screened interaction. Why do we know that? We know that because we can do even more enhanced calculations by switching on these ladder diagrams in the screening. So if we do that, if we include these ladder diagrams in the polarizability, the band gaps are really going back to the agreement with the experiment. So yeah, we again back to the red line. The question is now, why is the Kohn-Sham screening, in particular self-consistent GW, better than fully self-consistent GW? The simple answer is actually fortuitous error cancelling of Kohn-Sham DFT, and that is demonstrated with these values in this table. So here we have the macroscopic dielectric constant for various GW flavors and compare it to the experimental results for some set of systems. In the first column you have the results for the self-consistent GW, the fully self-consistent one. Then here we have the GW, but with the ladder diagrams included in the screening. And this column contains the Kohn-Sham results, so the RPA using Kohn-Sham orbitals and energies. And if you compare this one to experiment, it's actually better than the self-consistent GW results. So how can we understand that? Can be understood by noting that the Kohn-Sham band gap is smaller than the one of the self-consistent GW method. So meaning that the Kohn-Sham polarizability is larger than the screening of the GW one using these quasi-particle energies, which in turn means that the macroscopic dielectric constant is larger for the Kohn-Sham method than for the GW method. However, if you include vertex corrections you have really good agreement with the experiment, and that proves that you have to include more diagrams in the expansion. So which terms in GW do we neglect? So which terms in the GW self-energy, to be precise, are neglected? And the short answer, actually a lot. So even the second order terms like this second order exchange term are swept under the rug, or third order terms like these ladder diagrams are neglected too. All in all, you can class those missing contributions into two subcategories. One would be that describes second order exchange, and the other one which describes the electron hole ladder diagrams. So second order exchange has unfortunately no simple physical interpretation. They correspond to vertex corrections in the self-energy. And it is known that they are important to remove self-detection errors. In contrast, the electron hole ladder diagrams can be interpreted as electrostatic interaction between virtual electrons and holes. So they account for excitonic effects, and they describe corrections to the vertex in W. So they are therefore important to remove self-screening effects. And as a facet, GW is again an approximative method, so it's not the end of the story, because two main contributions are neglected. On the other hand, I would say the best practical approach right now is to either use this eigenvalue G0 W0, eigenvalue GW0, or even the quasi-particle GW0 approach on top of PBE, only if PBE yields reasonable screening. If you study larger systems, like larger unit cells, you could use the corresponding low scaling implementations where you just leave out this EV in front. However, if the screening is not that good, you could try to do this. You can try to do GW or single shot GW on top of an hybrid. Okay, but bear in mind, strongly localized states are probably most. So that means strongly correlated systems are most are probably still wrong. So time for questions.
Great, thank you very much for this extremely quick introduction to quantum field theory, and then dive right into state of the art. So I want to invite everyone to ask questions in the Q&A window. I think everyone is still a bit digesting, so I will take the opportunity to ask something. You introduced the concept, or you actually showed how to derive the Dyson equation
Yes.
with this geometric sum series. And I know that for the self-energy, people usually say, okay, this must be a small correction because we are already so close to the truth. So this self-energy must be small and this series will converge. Now for the RPA, you showed that the same argument is made for W. And I wonder, is the polarizability also always supposed to be small?
That's a good question, but I know what for sure that it's not true if you consider metals. So if you consider metals, actually, you really have to take care with how to deal with this. For the polarizability, frankly, I don't know. I know that if you compute the total energy using these two diagrams here, you will definitely get the dominating contribution from the Hartree term and the next one from the exchange term. So If you compare this maybe to quantum Monte Carlo results or CI, I would say full CI results for total energy for simple systems, you will see that you're not far off. So yeah, but the good question is, are these individual terms small? No one knows for sure, I think. It's yeah, this is the weak point of this theory, definitely. Good that you're asking really
it seems to
really good
work in
question.
practice.
Yeah.
So
That's true. Yeah. But what I heard and what I've read a few times is that most of the time it doesn't pay off to include only one diagram. So it really where the theory shines is then when you can include all kinds of one specific diagrams up to an infinite order. And actually, as far as I know, the only thing where this works is for RPA. So, but I'm not sure in high energy physics, maybe those diagrams here can be included as well. So yeah.
Okay, so there are now a lot of questions from the audience.
Oh yeah,
let's
they're popping up.
answer them. Does the functional use during the DFT step have any impact, or does one always have to use LDA? Or yeah, maybe you can also comment on double counting.
That definitely has an impact because the band gap differs depending on which functional you choose. So, and the band gap is insofar important because it actually goes into directly the calculation of the polarizability, as you see here. So it's inverse proportional to this. The polarizability is inverse proportional to the band gap, and depending on which functional you choose, the screening will be affected. So, for instance, if you choose an hybrid one, you have a larger band gaps, the screening will be smaller, and vice versa. So that definitely is important. Yeah.
Great, thank you.
There's
sorry.
Double counting, yeah. Concerning double counting, yeah. So LDA and DFT and so on, they have, of course, pieces of correlation included in the functional. And typically, what I know is that quantum field theory starts with Hartree-Fock and then does all these expansions in diagrams in this Hartree-Fock basis, where you don't have then double counting. However, I can show you later in the second part for RPA that there are some contributions of diagrams that are usually not included in these expansions because people think that they are kind of zero, which is only true for Hartree-Fock. So in this sense, one can maybe deal with double counting, at least for the lowest order terms with this singles contributions. But maybe later in the second talk, I can talk more about this.
Great. Another thing that you mentioned in your talk is the scaling behavior of GW. So this, whenever we talk about scaling, it usually means something's very expensive to do, right? So
that's true.
How expensive is GW compared to regular DFT?
So it's actually exactly what's written here on the very first slide. So sorry about that. So here we have DFT. So this can be done. So the ground state can be. I don't know why my mouse pointer is lagging here. Sorry, but that can be done fairly quickly. So in VASP, I think you can do up to 1,000 electrons. But then if you go further, if you use hybrid functionals, it's already very costly. And with this low scaling GW, I would say if you compute the total energy, we have done calculations for up to 200 atoms in a cell for running one. So I think 1 hour on 128 cores. GW is slightly more expensive, so probably I would factor that by a factor of 4 in time. But I think it's doable, yeah. So this is kind of the what you can do with this algorithm. Yeah.
Great. So you first have
Okay,
to consider
maybe
how much there's for the computational cost, right? Where you can bear that for that system.
That's true. As for sure, you can't simulate I don't know, phase diagrams of really big cells and so which you need. You can forget about that. Yeah, but yeah, as I said, so for instance, defect formation energies for silicon can be done. Yeah, maybe some attendees have a good idea what to do with the algorithm. That would be nice.
There's another good question. How well does the GW method perform for surface science, given the context of the issues highlighted with hybrid functionals yesterday? So we talked about.
Okay, so surface science is actually where GW and especially the related RPA, so the method how to calculate the total energy. So this talk was only about the band gap, right, and how to get spectral properties out of the Green's function. But in the second talk, I will talk about the total energy, how to get it from this approximation. And in fact, this is where actually this theory really shines. So I will show you some results in the second part, where one studies, for instance, the CO molecule absorption energy on metallic surfaces. Yeah, you will see.
So maybe again to point out the difference between the various GW methods. How would I choose which GW to use for my system?
Smaller systems, especially those in the lecture, so in the hands-on session, they are really the best done with this quartic scaling. So very small systems, like if you have only 2 atoms or something similar, you should do a standard GW without doing the low scaling approach. The reason for that is actually quite simple. The low scaling approach has a lot of FFTs. You need to perform a lot of FFTs. So FFTs scale basically linear with the number of the system size, but it comes with a huge prefactor. And every time you perform this huge prefactor slows you down. And that's why smaller systems should be really studied with this quartic scaling GW. So let's say the old implementation under parentheses. It's yeah, but as soon as you have larger systems, like as I said, roughly 20 more, I would go over to the new scaling, to the low scaling approach. Bear in mind also that the new scaling approach, I'm always saying new, sorry, it's the low scaling approach requires relatively lot memory storage. So you need really a lot of memory. And that means also that you might even need more compute nodes to satisfy this demand. Yeah. And so yeah, this is what I can say without knowing how the system really looks like.
Then there is another question about magnetic systems. So how successfully does the GW approach treat the triplet states? Is spin contamination something to be concerned about in the GW approach?
Sorry, that's something I have to pass this question. I don't know exactly. What I know is that the old, so the quartic scaling GW implementation, so the implementation recommended for smaller systems, has actually a spin included. So you can switch on spin dependence. You can even study spinors, or let's say spin orbit coupling. However, for this, the low scaling approach doesn't have this feature yet. We are planning to implement this, but it probably will take a while. However, how this contamination with the triplet states looks like, honestly, I can't answer this. I don't know. Sorry,
very specialized question. So from the same person, actually, there is a question, a very practical one: can consecutive iterations of the Green's function in the eigenvalue GW0 approach be achieved in multiple runs?
Yes, it can be. That's a good question. It can be, but you have to do a preparatory step after the DFT. So after you have done the DFT step and increased the virtual space, you back up the wavecar and the corresponding waveder file by adding an extension .chi with small letters. So you copy wavecar to wavecar.chi, and you copy waveder to waveder.chi. And this will then tell the algorithm to use the screening from these files. And these files correspond to the screening of the Kohn-Sham wave function, right? Because the reason is, after you've done one loop in the GW, you will get a new wavecar. And then if you repeat this, if you restart the calculation, and restart the GW step from this wavecar, you will actually recompute the screening. And that's different from the screening in a self-consistent scheme where you freeze the screening. Is this helping? Yeah.
I think so. Yes.
Yeah.
That cool. We can close this this lecture on schedule, and thank you very much for this great talk.